And so these are the two items that we're going to cover today. So a permutation is when you start with a group of elements and you rearrange them. So they start with a specific ordering as the top of the screen. And we can, if we move them around to a new position, this is a permutation of those elements. So that's the word permutation. So it's a set of distinct elements, and this is an ordered arrangement of them all. So each different ordering is a permutation of that set of elements. If instead you want to take a subset of those elements, so R elements, it's called an R permutation. And what that means is R is a number, right? That's just a variable that I'm using to say this is how many elements I'm going to take from that set. So if, for instance, I started with the set A, the ordering A, B, C, D, then a permutation of that would be if I reverse that. So D, C, B, A. Oh, it really is more than just my pen's battery that causes this issue. So if I wanted to take a 2 permutation, it's all the different ways. Those are the permutations that involve 2 of those elements. So AB, AC. And in this case, BA is different. I think I need to replace something about this pen. Maybe the pen itself. Okay, so let's take a look at some examples there. Well, or overwrite them. So one example is if we look at the set 1, 2, 3. So n ordered arrangement of that is 3, 1, 2, right? I can rearrange those. And in the set, order doesn't matter. So these are really, they're acting like sequences, 3, 1, 2. But oftentimes we just write it down as 3, 1, 2. And so the ordered arrangement 3, 1, 2 is a permutation of S. And it's not you could call it a 3 permutation if you wished, because it contains 3 elements. But typically if it involves all the elements in the set, we just call it a permutation. So if I ask you for a permutation of those elements, I'm asking you for all of them. Okay? On the other hand, 3, 2, you'll see they're elements from that set and they're ordered with 3 first, 2 second. This is called a 2 permutation. It's some way that I can manipulate and organize those elements. Choose if I only am permuting 2 of them. Okay. So the thing that we're talking about is not really permutations, right? We're talking about counting. And so the thing that we care about is the number of these permutations. And if I talk about the number of R permutations, that can also include permutations of the whole set. In this case, if I have n elements in a set, then if I want to talk about a standard permutation, it's an n permutation. I'm going to take all the elements and I'm going to permute them. Okay, and so the reason that this matters is when we can challenge Brent to think about times that he's used permutations in programming, but is if you're trying to figure out the number of ways that you could combine different things, right? So you have arrays that you're working with, and you want to think about the number of ways that you could reorganize things. You might need to know that for a calculation within a program, okay? Brent's, I can see his wheels turning. When have I done this? I know, but we're asking him near finals of his last semester, so we won't actually challenge him unless he has something to add.
I do actually have one situation.
I could see the wheels spinning.
Yeah. My fiance works at St. Mary's, so she works with fish biology, and I won't pretend to understand most of what she does, but she does some sort of thing that she has to have all the combinations of male to female with this species and that species. So she asked me to write a script for her to figure out all the possible combinations, so she didn't have to do it by hand because there's 400 possibilities. So yeah,
that's awesome. And so if you were writing a program to actually output the possible combinations, you would actually have to identify and be able to generate those combinations, which is really cool. Also, I do have to point out that the chat is saying fiance. That's big. Yeah.
Yeah, that was a few weeks ago, actually.
Yeah,
So.
it's still news in our chat room. That's amazing. Yeah. And congratulations.
Thank you.
He's just going out with a bang this whole, like, finishing
That's
up
right.
his degree, getting married one day. Awesome. Congrats.
Thank you.
Sorry, I know we could be off track for that for a while, but okay, so if we want to count the number of those, the way that we represent that is, come on. Oh no. Honestly, I swear, I think, hold on one second. We're going to try something else. Do we think this has any batteries in it? I do actually have a backup. And you've lost me. Don't worry. I'm still here. I completely lost my pen now. We'll give it a go. See if this works. Okay, maybe it's working. Can you still see the screen and everything?
Yeah.
Okay, I disconnected it for a second. So, all right, we'll see. So, what we want to look at then is the number of possible permutations of fish species. And if we want to do that, first we start out with the number of elements total. And we want to say, well, how many elements are we including in that grouping? So, for instance, if in Brent's scenario, and I will pretend to know very much less about biological oceanography or limnology or whatever it is that she studies. Is she freshwater or saltwater or both?
Brackish water. So
brackish. There you go. The mix of the two.
That's right.
Yeah. All right. So if say there were 50 species, 50 different species of fish, that's our N elements. That's how many we're choosing from. And I assume in this scenario where we're looking at combinations of what they can produce, we're going to be choosing 2 of those. And so we're looking at 2 permutations from that set of 50. So how many different ways can we combine those? Looking at a simpler example, we could be looking at 2 permutations from our simple set, which includes 1, 2, and 3. And if we look at all the 2 permutations of that, you can see that there's 1, 2, 1, 3, 2, 1, 2, 3, 3, 1, and 3, 2. And in the last lecture, we talked about tree diagrams. This is one of those simple ways that a tree diagram actually does work out in your favor, right? It's pretty easy to say, okay, the first one is 1, 2, 3. 1, 2, sorry. I can't choose the same one again, so there's only 2 each time. 1 and 3, 1 and 2. We could easily list off, if anybody could read this. We could list off all the possible combinations using a tree diagram. So you think about all that's left and say, okay, it's 1, 2, 1, 3, 2, 1, 2, 3, 3, 1, 3, 2. There are a lot of ways that you can just make sure that you don't miss anything. But this is one possible tool in your tool belt. Okay. But mostly what I care about is how many there are. So I can list it out like this. I can use a tree diagram to help myself. I can write them out in a way that makes sense. There's a lot of different techniques. But what I actually want is that number. So how do I quickly get at this number, that the number of permutations, starting with 3 elements, taking those 2 permutations, so that's that P32, is 6. It looks like I crossed that off, but actually wow! Maybe this is why my pens don't fly. You should see me when I have a whole room to use. Boy, disastrous. P32 is 6. So there is a formula because we care about this. This happens a ton, right? So I have no idea why that goes off the edge of the screen. But if n is a positive integer, it just says r, okay? And r is an integer somewhere between 1 and n. And, every time you see something like that, you should think to yourself, do I have to remember that, or is there a logical reason there's a bound on that? Well, remember, r is the number of permutations. You're either going to choose 1, or you're going to choose all 2, 3, 4, all the way up to all the elements in the set. So r is bounded just out of logic. We could include 0, except this formula doesn't work. And so we'll give you a special formula for 0, but I think you can come up with it yourself. So we'll get there. Okay, so this is the number of ways that we can choose those elements, and we can permute those elements. And we've kind of looked at this, right? This idea of, well, how many ways can we select the first element? If I was drawing out the tree, that first row of that tree is 1, 2, 3, all the way up to n, right? We'd include everything. And the next level down in this tree, if I'm going to choose, this is going to be, r rows down, or r, the depth of this tree is going to be r. The next level down, each possible option, like if I look below n, it can contain 1, 2, 3, all the way up to n minus 1. But it's going to include everything except whatever was on the leaf above it. Okay, so the next level down, for every n of those first choices, the next choice, there's only n minus 1 available to us. And the next one after that, I won't be able to choose the ones that have already been picked. And so n minus 2. And I keep doing that all the way down to that last row. Again, we'll prove that, but this is actually the formula for the number of r permutations from a set of n elements. And importantly, n distinct elements. So if there's a repeating element in the set, we wouldn't count that. So the idea is exactly what we looked at last time. To do this, we use that product rule. And I've sketched that out, but the idea is exactly what we did before, right? The first element can be chosen in n ways. So essentially what we're doing is we say, right, I'm going to pick, assuming our set, let's for ease, are the integers 1, 2, 3, all the way up to n. I'm going to pick 1, 2, 3, all the way up to r. I want an r permutation. So I have to choose what I'm placing in these positions 1 through r. So the first element, I can choose all of them, right? This is the number of ways. So I have n choices. And then for this position, how many ways do I have? So for the second element, how many ways can I choose that? Yeah, n minus 1. I can choose everything except whatever it is I chose in that first position. And for the third, I can choose n minus 2 because the only ones that I will avoid are anything that came before it. And the same is true until right here, right? And this last element at this point, and this is this off by 1 error that we talk about so much in computer science, I'm sure in 1105 and 1110. If you're taking those right now, you talk about off by 1 errors. They're easy to inflict. And they come from things like this. It's really tempting to say that the number of choices, so there's n minus 1 choices here, n minus 2 here. It's really tempting to say that right here, there's n minus r. But there's not n minus r, right? There are only r minus 1 choices up to this point in time. And so it's really n minus r minus 1, which is why we see this piece here, this n minus r plus 1. It's really n minus, this here is n minus r minus 1. Okay? That's where that comes from. And I'll clear up my screen. There you go. So in the second, there was n minus 1 ways, and so on, until finally there are n minus r minus 1 ways to choose that last element. Okay, so that's sort of the proof. And then we can stick our... Oh, you'll notice in my last solution I put the actual Helmholtz symbol. But it's good to know what that is. That's the actual proof symbol. That's the boring one. It's called Helmholtz. I can't write apparently that quickly. Okay, so then the question that I have for you is, well, what if, so this only works for 1 to n. So I didn't give you when r is equal to 0. So what is p n 0? How many ways? What is p n 0? First of all, what does that mean? Like in plain old English, feel free to use your mic. What does p n 0 mean? Yeah, Adam, how many ways can I choose the empty set? How many 0 permutations are there?
The 0 permutation.
Yeah, the 0 permutation. Which is like saying, how do I pick the empty set? Yeah, and so I see a couple answers. I would like to do the following. How many people think there are 0 ways? Raise your hand. A few. Okay, we're getting there. This is a class. I'm giving you 2 choices. I'm giving you 0 or 1. So we've got a couple. How many people feel that there is 1 way, exactly 1 way to choose the empty set? Oh, it's building quickly. I'm going with the masses. So in fact, there is an empty set. So there is at least 1 way to do that. And in fact, there's no other permutation of 0 elements. There's only 1 permutation. And it's a little weird to think about, but this is 1, and it always looks like this, right? It's always the empty set. And so it is defined, but there's only 1 way to order 0 elements, which sounds weird because there's nothing in there, but there's an ordering. It's just always the same. It's the empty set. The way is no ordering. So here's a corollary of that. Yeah, that's a good question, Adam. Does anyone want to take a stab at this question? Why don't we count that as a permutation of P in other methods? So like you're saying in PNR, Adam? Or maybe I'm misreading the question.
Yeah, I'm saying like, yeah, if we had 1 or 2 elements in our set, why aren't we counting that as a permutation?
Perfect.
If we're not looking at permutations of just 2 or 3 elements or something like that.
Yeah, that's a very good question. Shelley, go for it. Convince us.
Oh, sorry, would it give us an off by 1 error? So we ignore it for our convenience?
That's a good question. Well, this is going to come back to, actually, it's a perfect question, Adam, because it points to one of the things that did drive a lot of issue on the test regarding sets. So the question is, if we look at a permutation, let me see if I can find real estate somewhere. I'll just get rid of things and make myself some space. Okay, so if I have a set, not for ease, my pen's sake. If I have a set 1, 2, and 3. and I take a 2 permutation. I think what's being asked is this. Actually, let's do it even further. Let's make it even easier for us to think about. If I have the set containing just 1 and 3, or whatever that looks like, 1 and the symbol that used to be 3, then if I want 2 permutations, I think the question is, should I include, so should it be 1, 3, should I also include 1 empty set? Right? Like, is that supposed to be in there?
I kind of understand it here, but I'm more so wondering, like, if we're looking for the permutations, all of the permutations, like, not just the second order permutations or the third order permutations. If you know what I mean?
No, I don't know what you mean.
So, like, we're looking for all permutations of that set. So, like, 1 would be a permutation of that set. 1, 3 would be a permutation of that set.
Yeah.
Then would it get counted?
No, and so, sorry, I didn't write it all out, but I think the question, so if I had 1 and 3 in my set, I think what you're saying is, like, when I draw out this diagram and I say there's 1, 3, and then this is 3 and 1 is all I have, right? Why is it that I don't say, what about this? Is that what you mean?
Yeah.
Okay. This is I think we're going in the same direction. So I was looking at the possible 2 permutations, right? And so the question is, why am I not including this? And this is actually a question back to everybody. There's a very important reason that I'm not. So if you think you know, you might be right. I couldn't even bring myself to draw a line. I had to do a dashed line. So it's a very important question, Adam. I think there's an answer. So your 1 empty set feels like a 1 permutation and not a 2 permutation. Okay, so if the empty set is in the set, we should include it. But what can you tell me about the empty set? Let's call this set S. Ugh, let's try. So let's have a set S. And this is our 1, 3. And so tell me this. Which of these, is this true? This actually got more than a few people on. I like the no question mark. That's, I think, where people are at with this. So could somebody also put a yes in the chat, maybe Brent? And then give a thumbs up on the one that you think is true. Yeah, so Adam beat you to it. So
Yeah, I see that.
yeah, so like the one that you think is the right answer. Give a little thumbs up to the no or the yes. Is this true? Yes or no? You can choose Adam or Brent and can add them together. It's like a, I don't know, a popularity contest going on over here.
I won't take it personally.
Well, they're going for you, Brent, so
Yeah, we can cover that.
Adam shouldn't take it personally. Okay, so we're very split on this. And this makes sense to me, given the fact that on the test, there was a lot of confusion about this particular thing. Now I want you to unlike those, or maybe Brent can give us a new yes and no.
Okay.
And then I will say, how do we feel about this? So the new one is this guy right here. What about the empty set as a subset of the set? We're feeling a bit more together on this particular topic. Okay, so this one seemed to be well understood on the exam. This one did not. And I think what we're seeing is that's playing out here. But we were basically split 50-50 on this part, but this one you got correct, right? Yes, the empty set is always a subset of every set. Okay. However, and in fact, because I use equality here, now it's not always a proper subset, because a subset, it's not a proper subset of the empty set, but it's always a subset of every set. That I can safely say. So you guys are spot on with that one. But this first piece, being an element in the set, is different than being a subset of the set. The empty set is not in there. It's a subset of what's there. You can choose the empty set from that set, but it's not an element in the set. Okay? For it to be an element in the set, I'd have to have like a set A, and it would have to look like this. 1, 3, empty set. It has to be in there. To be a member of the set, it has to be one of the elements. The empty set is a subset. So if I draw my Venn diagram, I can choose this tiny little piece of nothing. If 1 and 3 are the only things in there, I can choose to take this little subset which doesn't contain either of them, but I can't actually grab the empty set because it doesn't exist in there, which is very messed up and confusing. So the number of 0 permutations in any set is, I'm reading Adam's message, the number of 0 permutations in any set is always 1. Sorry, it doesn't show me the bottom. 0. Because the empty set is there. Yes. It's not that it's there. Okay. So, here's an example. If I wanted to look at the number of 1 permutations of this set, I can choose to select the 1. I can choose to select the 3. There's 2 different ways I can do that. If I choose to select 0 elements, so looking at a 0 permutation, then I have one way to do that. I select none of them, and the result is the empty set. It's not that I'm choosing the empty set from that, but actually the set that I get is equivalent to the empty set. There's nothing in it, which is different, right? Okay, and we can, it's a kind of an interesting topic when you come around to it. All right, so essentially what we said then, and the reason that this is a corollary that we don't have to prove, is remember, if we from what we came up with, the number of R permutations was n times n minus 1 times n minus 2, all the way down to n minus R minus 1. Okay, so we multiply all of those together. And you can show to yourself that that's what you're getting here. Because n factorial, remember, is n times n minus 1. Oh my, this pen is going to kill me. N minus 2, all the way out to n minus R minus 1. And then it's just going to keep on going, isn't it? But I'm going to stop there and say, okay, after that, it's n minus R and everything below it multiplied together. But I'm just going to call that n minus R factorial. And so if I put this whole thing, this is n factorial over, this was n factorial that I just wrote out, right? So then if I put an n minus R factorial on the bottom, what happens there is I just remove, they cancel each other out, don't they? And so what I'm left with is actually the equation we had on the previous page. But this is an easy way to write it. And it's an easy way to calculate it. So if I was going to concoct the number of permutations, I would make sure that I knew how in Java or any language I'd know if there was a math function, math method available to me from the math library, or I'd create my own method to create a factorial, right? That's an easy loop. You've probably already done it in 1105 or 1110. But working with factorials, it's just, loop from 1 to n, multiply everything by each other. Okay. And so this is an easy calculation. Now I just have a method that says the factorial, n factorial over n minus r factorial. So let's apply it, because now we've got a nice simple way to do this. So let's count some permutations. How many ways are there to select a first prize winner, a second prize winner, and a third prize winner from 100 different people who have entered a contest? So this is not written as a permutation. I didn't ask you to tell me what is P, N, R, but the first problem you have is, well, what's N? How many elements are in my set? And this is going to be the fun part on the assignments, is figuring out which do I apply, right? So we've got answers of 100. Oh, we've got a few, yeah. So I also see 3, all good fun. So why is it 100 and not 3? Somebody who answered 100? Kun, Schwan? Whoa, goodness me. Okay. Does anybody want to answer? Feel free to use your mic. We want all the elements in the set as n. That's right. And what is my R? What type of permutations am I looking for? 1 permutations, 2 permutations, n permutations. R is 3. So R is 3. I'm looking for the 3 permutations. How many ways can I put the first, second, and third prize winners together? So what I'm looking for then is, and it says how many ways. So first thing you do when you look through a question is you identify, what is the problem I'm solving? I've got a set of 100 elements. I want to find the number of ways that I can pull 3 of them out and permute those names. And so what I'm looking for is that P100, 3. Okay, so what's my solution then? I think somebody had the answer already. Remember that we want 100 factorial over 100 minus 3 factorial. 100 minus 3 factorial. Or 97 factorial. See here, yeah. Okay, so add them. 100 over 97 factorial. Exactly. And that's the same as 100 times 100 minus 1 times 100 minus 2, or 100 times 99 times 98, which was this answer. Okay, 970,000. The alternative way that you could have represented that, so this is legitimate to take 100 minus 1, 100 minus 2, but alternatively, we could also have written that, as was done in the chat, as 100 factorial over 97 factorial. And remember, what this looks like is 100 times 99 times 98 times 97 factorial over 97 factorial. So these cancel each other out, and what we're left with is the same answer. When we see the word corollary, you'll remember from proof, the proof is proving the fact. A corollary is, I like to think of it as a freebie that comes along with the theorem. So you prove a theorem, and then the corollary is like, here's a fun extra. You got this one for free. So it means the same thing. You don't need to prove it because it's kind of a result of the original theorem. Okay. So here's another one. Suppose that a candidate, we all saw this happening in the States just recently, is visiting 8 different cities. So they're off to kind of get their people to vote for them, rally the troops. So they must begin their trip in a specified city, probably because they live there or started there. Okay, and they can visit the 7 other cities in any order they wish. So how many possible orders can they use when visiting these cities? Now, Side note, there are a lot of people writing programs like this because it costs money, it takes time, especially politicians that are trying to go out and visit these people, right? It takes a lot of time to go from place to place. So they want to look through all the possible combinations to find the one that is the shortest to preserve that time so they can then go blitz another 6 cities in the other direction, right? So how many possible orders would you have to look through in order to make sure you found the smallest route? Okay, so starting our solution, the first city is chosen, and there's a fun hint. The rest are ordered arbitrarily. So I'm going to list off my cities here. City 1 is set for me. We see a few different questions. Well, how many ways do I have to choose the next one? So I've got eight different cities to visit. The first one's chosen.
Is the first one always the same city too, or is it
It's
different?
always the same. Yep. Because it's where they're starting. So they're just going to start in the city they're at. It's not going to change. The first one's specified. So I see Daniel, Adam, a few others have been suggesting 7 factorial. And why? How many choices do I have for city number 2? Yeah, 7. And then I have 6. And then I have 5. And then I have 4. Well, okay. Why is it that this is why is this under permutations? It feels like something that I just could have come up with before, right? So I agree. Your ordering is right. There's 5,040 options. 7 times 6 times 5 times 4 times 3 times 2 times 1. How is this a permutation? What is it that I'm actually asking for when I'm asking for this piece? Because we were able to kind of reason out the number of options. So if I said, well, what's n in this scenario? A was given. So really the decision point was right here. Yeah, so n was 7. I had 7 elements, 7 cities that I had to choose amongst. And how many permutations were I looking for? What was my R? Here's the hint. This is going to be equal to, so how many combinations was I actually looking for? I needed all of them. So this is one of those times where R was also equal to this. So P7, 7. I wanted all permutations. And so this was equal to 7 factorial over 7 minus 7 factorial. Uh-oh, what's that? 0 factorial, that feels wrong. Don't get nervous. So 7 factorial over 0 factorial. That feels like we're dividing by 0. Is anyone scared? But Adam is absolutely right, as is Daniel. Don't be nervous. 0 factorial is defined to be 1. Okay. So this just becomes 7 factorial, which gives us the answer that you all came up with. So everybody's on the right track. Okay, so what that means is if they want to find a tour with the shortest path that visits all the cities, they have to consider 5,040 paths. It's a lot. All right, which is why we use computer systems to do these things, because that's too many to write out by hand. But you can write a program to do this. Okay, so here's another thing to think about. So how many permutations of the letters A through H contain the string ABC. And this one's a fun one because now I want you to think about what are you going to use for N and what are you going to use for R. I'm already giving you the hint that it's a permutation, right? I asked how many permutations. Now this is one that you might not think about in this way. So Adam says 6, which is fun. And yeah, so Adam, do you mind turning on your mic and telling us why 6? Because I can count, I know E is the 5th letter, so I know I have more than 6 letters, so why 6?
Well, our string is 3 letters long, and our base set is 4, 5, 6, 7, 8 letters long.
Yeah.
So there's only 6 different ways we can fit A, B, C in there in order, without breaking that string apart.
That I think you've just identified the kicker. You're treating, I think, ABC as one element.
Yeah.
Yeah. So, and this is a fun trick. Okay, so you might be thinking, that's spot on, Adam. Really nice answer. So the trick is to say, well, you know what? I'm just going to treat ABC as one choice. It's going to take up 3 spaces, but that's okay because I'm just looking at how I can order these things. So if I choose ABC as one block, it's like if I had Lego pieces and this one just happens to be a 3 instead of the tiny little ones, right? It's okay. What order do I put these blocks into this space? And so how many ways can I mix up D, E, F, G, H, and then this one block of 3 letters, A, B, C? So it's a permutation of 6 objects. And I want to use them all, right? I want the full permutation. So R is equal to 6. And we know in that scenario, it's 6 factorial over 0 factorial, or we can just say 6 factorial. And so there's 720 ways we can do that. Okay, so now next to a new word, combinations. So an R combination, so this is again choosing a subset of things, is of a set of unordered, of a set of N elements, is an unordered selection of R elements from the set. Okay? So the idea is that in R combination, it's really a subset of the set with R elements. So if I said, well, what's a 0 combination? Still the empty set. Okay? And just as we had P and R for permutations, we have a phrasing for this. We use CNR to mean that we have a combination of R elements from a set containing N elements. Okay, so we're looking at all the possible subsets of a set containing, all the possible subsets containing R elements from a set containing N elements. The other way that we, and we will come back to this next week, but another way that we refer to this is as a binomial coefficient, and we use this notation and choose R. But we'll come back to that. For right now, can sort of stop here. We're going to use CNR today, but I just want to tie those two together. Okay, so possible combinations. If we have a set A, B, C, D, then we can have several 3 combinations. One of those is ACD. So it's just pick 3 from the set. So if there's any subset, you're looking for all the subsets. So if we have a set S, it's all the subsets S such that the cardinality is equal to 3. Okay? So it's all those subsets with cardinality 3. And one of those is this subset ACD. Okay. This is the same. So unlike a permutation where that order is everything, ACD is different than DCA, is different than CDA, is different than ADC. Sets are different, right? So ACD is the same as DCA. Would this be like cardinality of a power set? It's just the basic cardinality of a subset. Yeah. Yeah, so ABC is just a package. However you put it together, it's like if you get a bag of groceries at the grocery store. You putting them in a different order doesn't matter. As long as you get home, you can still make the same meal. Sorry. So if I say C42, that means I've got a set of 4 elements, and I want to pick a combination of 2 from that set, and this is going to be 6, because the 2 combinations of S are the 6 subsets as follows: AB, AC, AD, BC, BD, CD. Okay, and you'll notice if I was talking about permutations, 2 permutations, then I would also include BA, and I would also include CA, and I would include DA. But with combinations, they're the same thing, so I don't include them at all. Okay? So we want to count these things. So we need a formula. And the formula, the thing that trips people up is that it's very close. But we have one fancy new guest in this equation, which is that extra r factorial. So it looks very close, except you have an r factorial. Oh, Anik, totally true. Don't put the milk on top of the eggs. Other than that, the order doesn't matter. Well done. So if you're trying to remember these formula, which I always suggest, don't bother wasting brain space on formula that you can look up. This is why I generally would be happy with OpenNote in this scenario. The most important thing to remember with any of these is, why would I use one versus the other? Okay? That's what matters. Don't waste energy remembering formula, except it is important to note that they're very similar, but they are very different. And you have to know when to use one versus the other. So the number of R combinations from a set with n elements, and again, we're placing R somewhere between 0 and n, is the following: n factorial over n minus r factorial times r factorial. And the proof for this is as follows. By the product rule, so breaking it down, this is an interesting piece. What happens here? Why does the product rule apply in this way? So I'm not applying it to this. I'm actually using the product rule, and this is what we just looked at. The number of permutations. So I've got n elements, and I want to permute 4 of them. I want to find all the R permutations. Why can I how do I use the product rule in this scenario? What is this saying? It's saying a lot. Now you're combining a lot of ideas. Take a moment.
I think it's saying like the number of different combinations and ways we can put the elements in the set together times the different patterns that we can actually put them in.
Exactly. And it's a lot like what we did on the previous page. So what does CNR mean?
Those are all the combinations that we could possibly get.
Exactly. And then PRR?
That's the orders of those elements that could be in a set of that length R.
Yeah, it's the total permutations of R elements, because if it's RR, it means now we're considering the set of R elements, and we're going to permute all of them. Exactly. So this one, play it out in small examples. But that's a very good summary of that. But if you need to see that, try it out with small n and r. Play with this, okay? Okay, so let me just delete this. So, but what that means is now we have a formula. We know the formula for PNR and PRR because we have it, right? We just were given it on the previous theorem. And so now we can just move things around, right? From this, we can get to this point. We just divide by PRR, and that gets us to this point. We know the formula from each of these to each of those, and then we can just simplify. And what we end up with is what we were looking for in the first place. Okay, so we're not going to belabor proof at this point. To some extent, you can take this for what it's worth. Proof is not the point of this section, but do step through it to make yourself believe it, especially going through small examples, and especially because we are talking about the product rule, and now that you have these two new definitions, make sure that you can believe this, okay? Because it's a simple piece, but once you get comfortable with combinations and permutations, that will make more sense. Okay, so here, let's go through some examples. That's what I care about the most. Anybody play poker? How many poker hands of 5 cards can be dealt from a standard deck of 52? And then there's a second question to this, but let's start with the first. How many hands of 5 cards can be dealt from a standard deck of 52? First of all, in this case, are we applying permutations or combinations? Does the order matter? Everybody moves their hands around in a very specific order when they hold them. Does that change anything? No, the order doesn't matter. I have a kid that puts things from like high to low, and I've got a kid that puts things from low to high, and others organize them by suit. So does that matter? It doesn't change my hand. I still have to play the hand I've been dealt. So really, the cards in my hand are a set, and I just get to work with those, right? So all that matters is which 5 cards do I have. So the order in which the cards are dealt doesn't matter. It just matters what I have in my hand. And so this is a combination. Exactly, Adam. So in terms of like N and R, well, what's N? So for this particular one, what's N? 52. It's the number of cards, the total number of cards. And what's R? Exactly. So 5. It's how many ways can I organize 5 cards in my hand? And so in this case, what I'm looking for is C 52, 5. So N is 52, R is 5. And so what we end up with is that we apply the formula from the previous page. So this is N factorial over N minus R factorial times R factorial. And this becomes 52 factorial over 47 factorial times 5 factorial. And in the end, what that looks like is 52 times 51 times 50 times 49 times 48. And this is really, to start off with, right, there's a 47 factorial here. And there was always a 47 factorial included, right? This really looks like that. And this would have been there. But I didn't include it because I know that those two just kind of went away, right? And so what I'm left with is over 2.5 million possible ways that you could be dealt a hand. That's a lot for 52 cards when you think about that. So if you do play poker, but there's some similarities, right? A king, if you get a set of aces versus a set of spades, you might not care if you have, if you have a flush or something. So there are some ways that if you're counting cards, you can equate things, but it's still 2.5 million cards, possible hands that you could be dealt. All right, so then the next question is, how many ways are there to select 47 cards from a deck of 52 cards? What's my N? My set of cards hasn't changed. 52. What's R? Daniel, nice. So I see Schwan has suggested that we are going to look at C of 52, 47, and who was it? I want to give credit where credit is due. Somebody suggested, is this the same? Daniel. And we see somebody maybe agreeing with you. Is this the same? Okay, Schwan is also thinking this is the same. It is the same, I think. How many people think it's the same? Raise your hand if you think this is the same. But I'm choosing 47 cards. I'm not choosing 5. Why is that the same? Argue with me. Why is it the same? Like, fundamentally, why is choosing 47 cards the same as choosing 5? Feel free to use your microphone.
Yeah, kind of going off what Anna said, like choosing 5 means we leave 47 out. So it doesn't really matter how many of the cards we chose. And because this is a combination, not a permutation, order doesn't matter. And because of that, they are equal.
Perfect. Yeah, and so here, I love that description. You're choosing not to pick 5. You're choosing the 5 not to pick. And in fact, everybody's right. Yeah, clearly you guys are on the right track. And if you look at the formula, the reason is clear, right? N minus R factorial and R factorial in this scenario, they're flipped, but they're equal, right? So we have choosing not to pick 5 is the same as choosing to pick 47. And so the different ways to select 47 cards from 52 is C5247, but that is equal to the same. That's the same as saying choosing 5, 52, 5. And so we don't have to do the calculation. Yeah, it is neat. And this is, in fact, a corollary. So it's a free, fun fact that comes from our original theorem. So if we have the same N and R that we chose before, then C N R is the same as C N minus R. From the previous theorem, we knew that this was the value for C N R, and we can stick the other pieces in, and you'll see that you end up with the same value. And so you can play with it. And this becomes N minus R, or R factorial times N minus R factorial. And so these are clearly the same. And so these two are equal. Okay, so that is a fun fact. So, and actually there's the wrap up. I think it's always important to conclude your proof. So hence, there we go. All right, so how many ways are there to select 5 players from a 10-member tennis team to take a very special trip to a match at another school? Especially these days, we're not going to take everybody if we can avoid exposing them. So I need to choose 5 players from my team, and they're all really good. So you might be thinking I should be taking Brent because he's probably a star tennis player. But nope, we're going to just be very equal right now. And are you not? The look on his face implies maybe tennis is not his strong suit.
Not my game.
Okay, so if I'm going to choose 5 at random from my 10-player set, I'm looking for 5-player combinations. So the number of 5-player combinations is what? Even, yeah, so Burnley's got it, N equals 10, R equals 5. So that's 10 factorial over 10 minus 5 factorial times 5 factorial. Or 10 factorial over 5 factorial over 5 factorial, which you can prove to yourself is 252. Okay, now we've got another one. A group of 30 people have been trained as astronauts to go on the first mission to Mars. Brent, are you signing up for that one? I don't know how people are signing up for this. As a side note, this just makes me crazy. Like the idea of then being basically stuck in space for the rest of time, even if it's successful. Like, I don't know. COVID has taught us nothing. Being around people is kind of nice. One-way trip, Burnley. Exactly. So we've got 30 people. That's our N, right? Trained as astronauts to go to the first mission of Mars. How many ways are there to select a crew of 6? This is the one where I want to be chosen not to go. Just in terms of P, C, N, and R, what would that look like? Yeah. See here. So that is absolutely 30,6. C 30,6. So we're choosing a subset, not a permutation. I don't care which order they get on the trip. They're going to be stuck on it for the rest of time anyway. It just matters that they're the ones on this vessel into space. So it's how I choose a group of 6. Order doesn't matter. So it's a combination. We're choosing from a group of 30. We're selecting a subset of 6 people. And so it's a combination, 30,6, which is 30 factorial over 24 factorial times 6 factorial, or 593,000. Wow, that's a lot given. It's pretty impressive that the number's that high, isn't it? That's it. I'm sticking around for, I am not sticking around for office hours today. And I did not let people know this on Wednesday. The leadership conference thing is going every Friday from now on. So I do have to choose different times. And I know it's only one more week. But are there other times that people would suggest that office hours would suit or fit better? If you suggest them in the chat, I can try to make it work. Like just say Monday morning, Wednesday afternoon. Tuesday might be a good day because it's the day that assignments are due. But maybe people would prefer it earlier than that. This is it for new material. This is our combinations and permutations. You've made it. There's only one lecture left. And then a big party on next Friday /review. Whichever way you look at it. I'll call it a party.